We are on our second last lesson of the unit, lesson 6, the sine law, and more specifically, we already did a review on the sine law, but we're looking at what the ambiguous case is. You would have seen this last year. So just to remember, the sine law states that for triangle ABC, sine A is over sine A equals sine B over B, which equals sine C over C, or you can have it that you put the side on top, so A over sine A equals B over sine B, which equals C over sine C. And remember, to use the sine law, you need two angles and one side, which is angle, angle, side, or two sides and an opposite angle, so side, side angle must be given. So if we look at an example, just to refresh our memories, determine the length of xz, so xz would be here, or you're also looking at y, or side y, okay, to one decimal place. So the first step would be finding this angle. Just because we're given two other angles, you know that triangles add up to 180 degrees. So you can subtract that 84 plus that 27 to give you 111. So then that angle there is 69 degrees. Okay, that would be your first step, because now you can see your side angle pairs, which you want. So we're going to use Z, and we're going to use that y ratios. So over here, you're going to do y all over sine of y is equal to z all over sine of z. We weren't given a side x, so we'd have too many unknowns if we use that one. Okay, so you're going to go and sub in your information here. Sine of 69 all over 4 sine 27. And then just remember that you're going to cross multiply here. Oops. So you're going to get y sine 27 is equal to 4 sine 69, and then just divide by that sine of 27. And then you're going to get y by itself, because those cancel out, and you should get approximately 8.2 centimeters for that side. Okay, so that is our example of sine law that we did on day 1 of this unit, so on Monday. So you should be pretty familiar with that. Here's another example, and this is where our ambiguous case is going to come in, but I'll show you why. Okay, so determine the measure of angle B to the nearest degree of A. So this would be side A, so it's 3 meters. B, so this would be side B. This is 15 meters, and angle A is 16 degrees. Okay, so you're given side angle. You're going to use sine A all over A is equal to sine B all over B, only because we don't have any information for C. Okay, so for sine A, you're going to go 16 degrees all over that 3 meters. Then we don't know what angle B is yet, and then side B is 15. Okay, again, cross multiply, so you're going to go 15 sine 16 degrees equals 3 sine B, divide by 3, divide by 3, and then those cancel out, and then your next step would be taking that inverse of this whole thing to get rid of that sine from the angle B. All over 3 is equal to B. Okay, when you plug that in on your calculator, you should get the inverse sine of about 1.378. But then when you take that inverse sine, you should get something that says error. So what that means is that this triangle has no dimensions and it actually can't exist. Okay, so no triangle can actually be drawn with an angle of A of 16 degrees, a side A of 3 meters, and a side B of 15. Okay, there are other scenarios. We can either draw two distinct triangles, one distinct triangle, or no distinct triangles. So we're going to get into examples of how that works, and then I'm going to show you a little bit of a shortcut as well. Okay, so your ambiguous case. If you have your fixed angle here, you will have a fixed angle. You will know a side and you will know a side, but it can be any of these positions. So it's not actually fixed. It would be swinging. So it could be here, it could be straight down, or it could come in here a little bit. Okay, don't worry too much about the diagram, but just so you know that you can like have this arm swinging, so it doesn't have to be drawn in one way. Okay, the word ambiguous means that it's open to two or more interpretations. Okay, so that's why we can sometimes get two distinct triangles, 1 or 0. If you're given two angles in one side, so ASA or AAS, the sine law will nicely provide you with one side. However, when you're dealing with side-side angle, here the sine law could possibly provide you with 0, 1, or 2 answers. So when you're given side-side angle, this is when you have to be careful using the sine law. Okay, so we're going to look at what the ambiguous case is, and we're going to see how many distinct triangles we can draw given these certain measurements. So you're going to draw out your triangle. It is giving us angle, or side A is 10. Side C is 16, and then angle A is 30. Okay, so here you're given side, side, angle. So what you're going to do is you're going to see how many distinct triangles that we can draw. But to do that, we're going to do our typical finding this angle C, because we have no information for B, so it doesn't make sense to find B. So we're going to use the sine law to solve for angle C. Okay, so you have sine C all over 16 is equal to sine of 30 degrees all over 10, just using your information there. You're going to cross multiply, so you're going to get 10 sine C is equal to 16 sine 30. Divide by 10, divide by 10. So C is going to be sine inverse 16 sine 30, all divided by 10. You should get that C is approximately 53 degrees. Remember, we want to round to our nearest angle, or nearest whole number for an angle. Okay, so then for our diagram, or our triangle number 1, we would have 53 degrees. And then you would be able to find angle B here by doing 180 degrees minus 30 degrees minus 53 degrees. And then you would have an angle of 97. So that works out perfectly. You're able to draw one triangle for sure. But now, we'll switch colors here. You always have to check if you can draw more than one triangle, and I'll show you how to do that. Okay, so using our cast rule and our related acute, one of our angles is 53, so that would be your related acute. It's also positive, and we looked at sine, right? So where else is sine positive? It's positive in that quadrant we drew it in, but it's also positive in that second quadrant. So you're going to have a related acute of 53 degrees in that quadrant. Then you need to find that principal angle by doing 180 degrees minus that 53 degrees, which gives you 127 degrees. Okay, now instead of it being the 53 degrees, you have the angle would be 127. So you need to see if you can draw a triangle. Let's go back here. We're going to see if we can draw a triangle that looks like it's 127 degrees here. Keep the 30 belongs there. You're still side 16, this would be side 10. Okay, and you have to see if this angle works out if you use that 127 degrees. So you're going to go 180 minus 30 degrees minus 127 degrees, and that equals 23 degrees. Sorry, I had to take that in my calculator. Okay, so that equals 23 degrees. So that triangle works out. This triangle works out. So there, your conclusion there is going to be, therefore, two distinct triangles can be drawn. Okay, so that one works out that you actually can have two answers, which seems like a little bit more work, but you always are going to have to check when you're given the side angle. You need to check. Okay, we'll go into another example, and you'll see the difference if you can't have more than two, or you can only have one or zero. Okay, so here we are going to draw a triangle. A is 20, C is 16, and that angle is still going to be 30. How many distinct triangles can we have for that one? So you're going to draw that one this time, and it is going to look like this. And then we're still going to find angle C. We're going to use our sine law again, so we're going to do sine C all over C is equal to sine A all over A. You're going to fill that information in there. Okay, remember to cross multiply. So 20 sine C is equal to 16 sine 30. Divide by 20. So then you're going to be left with C is equal to the inverse, sine inverse of 16 sine 30 all over 20. Okay, so when you do that, you get C is approximately 24 degrees. So you can fill that 24 in. Make sure that you can get an angle here. So 180 minus 24 minus 30 degrees. And that one works out to 126 degrees. Okay, so when you're going to do that, remember we need to now check for another triangle. Okay, so you have your related acute. This time it is 24 degrees. It's still going to be positive in your all quadrant and your sine quadrant. It won't change for these examples. So 24 degrees. Okay, find that principal angle. So 180 degrees minus 24 degrees, which is equal to 156 degrees. Okay, so then you're going to try to draw that triangle again. Obviously my drawings aren't that accurate. You still have all of your measurements here and here. So then you're going to try to find this leftover angle. So 180 minus 30 minus 156, which is equal to actually -6 degrees. You can't have a negative angle, so therefore only one distinct triangle can be drawn. Okay, so that is an example of only one triangle being able to be drawn. And then we'll move on to your third example. Exact same thing here. So side A is 7, side C is 16, and angle A is still 30. We're still going to find angle C, so same thing again. Should be getting good at this by now. So you're going to go sine C all over 16 is equal to sine 30 all over 7. 7 sine C is equal to 16 sine 30. Divide by 7, and then you're going to go sine inverse of 16 sine 30, all divided by 7. Okay, when you plug that in on your calculator, it's actually going to come up error, which means, therefore, no distinct triangles can be drawn. Woohoo! Okay, this one is an easy one. As soon as you get that error on that calculator, just like we did at the beginning of class when it came up with an error, that you can just conclude right away, no distinct triangles can be drawn. Okay, so this is in your textbook. I took a picture of it. This is actually a kind of a shortcut that you can use to decide how many triangles can be drawn. So if you're looking at a triangle and you've labeled it angle A, and then opposite of side A, and then B is here, or it could be C. When you're doing that, if you get that A, so this side here, if you get this side is smaller than B times the sine A, so sine of angle A, then no triangle is possible, and it would look like this. The drawing doesn't actually work. That swinging arm from the beginning of the lesson wouldn't actually touch down here, and it doesn't form a triangle. Okay. If A is equal to what B times sine A is, then only one triangle is possible. And if A is greater than B times sine A, then two triangles are possible. This is the ambiguous case. So this example is your ambiguous case where you actually have to have, where you actually can have two examples is where you get the ambiguous case from. Okay. So for example, if we were to test what dropped my pen, what A is, and if it's bigger or greater than B times the sine of A, then we're able to tell if we're going to be able to actually draw this and how many triangles there are. So you're going to do 6.6 because that is A, okay? And then you're going to do B, side B, 9.8 times the sine of 40. When you put that in your calculator, what do you get? You should get 9.8 sine 40. We should get 6.299 or 6.3. So 6.6 is actually greater than 6.3. So in that example, if you were to go back, it is A is greater than B, so you are able to draw two possible triangles here. Okay, again for this example, locate angle A. This is side A, and then this would be B. So you are going to figure out 14.4, which is A. Is it greater, less than, or equal to B times the sine of A? So if you do 16.8 sine of 68, you get 15.58 rounded. So it is greater than that 14.4. Since it is greater and you go all the way back, you're going to get this example here. So no triangles are actually possible there. Okay, so you will be asked to calculate that in homework and use this type of calculation, which is a little shorter than those examples I showed you before. Okay, so you're just going to practice your homeworks on page 17, number 1 to 15. Good luck. Let me know if you have any questions.